We have seen that if X has density, then for all A in R, probability X equal to A must be 0. Now, isn't that counterintuitive? Because we of course must have probability X in R is 1. So X has to be some value or other in R. X has to take some value or other. So if each value has probability 0, then how come the entire probability turns out to be 1? That should also be 0. So that might sound counterintuitive. Now you can think of it in two different ways. One, here is a line segment, it has a finite length, non-zero length. Now if I take any single point, then that point has length 0. And that is true for every single point. But the entire thing consists of only points. Then how can this have non-zero length? It is because this intuition that the total length must be the sum of all the constituent lengths works only when the number of constituents is countable. Here there are uncountably infinitely many points, so you really cannot talk about summing them. So whenever you have an uncountable space, then these two things can actually coexist hand in hand. The second way is, suppose I run the experiment behind X. Whenever I say X is a random variable, there is a random experiment sitting behind it. Every time you carry out the random experiment, you get one value of X. So I run that experiment and I get a value for X, call that value A. I get some number, right? So I will say that probability X equal to A must be positive because I have actually seen that value. So this event has occurred. But I have probability of X equal to A equals 0. So it's an impossible event. Then how did it actually happen? Now the way to explain this is, when I say I ran that experiment and got a value A, I actually mean I measured X to get the value A. Now whenever I am measuring anything, I am doing so only with finite precision. For example, if I am measuring this length with a scale and the precision of the scale is this, in that case I will always align this with the nearest mark and I will report it as 7 units. And even if I make it finer, it will be 7 point something, but it is always finite precision. So when I am actually saying I have observed X equal to A, what I mean is X lies in this neighborhood where epsilon is the precision, and I have made it closed because I am assuming that I will always round up in case I land exactly midway. And probability of that, by the way, is indeed positive. So when I am saying X equal to A, I actually mean this, which indeed has positive probability. A good way to get a feel for this probability is to draw this graph, A minus epsilon by 2, A plus epsilon by 2, and it is this area. Now remember, whenever we are talking about a random variable being continuous, we basically have in mind a very small epsilon. We are measuring it precisely enough, so very precisely that we are assuming as if we are getting the true value of the random variable. So epsilon is pretty small. So you can think of it as a little rectangle. Though this is curved, but when epsilon is pretty small, it is like a rectangle whose base is of length epsilon and whose height is Fa. From this we get an interesting intuition about the density. Fa is actually this area divided by epsilon, and you have to let epsilon go to 0 plus. Don't worry that I made this round bracket here to a square bracket. It really doesn't matter because we are working with a continuous random variable. Now for this thing to work, we need again that obvious thing, F must be continuous at A. This is not at all difficult to prove in general, but it provides a nice intuitive understanding of what density really means. So we may even think of this as Fa gives you a measure of how likely X is to be close to A. We may say FA gives an idea about probability X being approximately equal to A. Now do not get it wrong. I am not saying these two things are even close. This is always between 0 and 1, while this can be more than 1. What I actually mean is this. So you have to do this division by epsilon and this limiting process. In this problem, we are working with a random variable x which has this particular density. Now you have to find out this limit. First you have to guess it, what it should be. And then you have to actually compute it and check whether your guess was correct or not.